Hi everyone, my name is Antoine Chevrot and I am a PhD student at the FemtoST laboratory in Besançon in France. And I am going to present today an approach on improved testing of artificial intelligence-based anomaly detection systems using synthetic surveillance data. So to begin with, we will explain what is a false data injection attack in the air traffic control and vessel traffic surveillance area. Then we will show our training data acquisition. After that, we will have a look at our data generation for AI-based model testing. From it, test datasets are created for the machine learning-based FDIA detection models. It's going to be our use cases. And finally, we're going to be talking about ongoing and future work. The ADSB protocol and its equivalent in the VTS, the AIS, were not really designed with security in mind. Indeed, all messages are sent in clear text as the features no encryption, no authentication. This means that anyone with the right equipment can listen, block, or with a little bit more of equipment that costs a few €100, can inject fake messages and even alter incoming genuine ones. This is what we call false data injection attacks. So we define a false data injection attack, so FDIA, as a combination of basic illegal operations, listening, blocking, modifying, and creating messages to alter the consensus reached by the nodes of a network while preserving the logic of the communication flow. This term was coined in 2004, where the FDIAs were studied in the domain of wireless sensors. Then a lot of work in the smart grid security, where the power system state estimation outputs can be corrupted by injecting false data into meta measurements. Another study shows that FDIS can manipulate electricity price market. So in the ATC domain, several types of FDIA attacks have been reported in the taxonomy. So we can talk about the ghost aircraft injection, that is creating a fake aircraft in the air. Ghost aircraft flooding is the same idea. Instead, we create several ones to flood the ATC. Virtual trajectory modification is a modification of trajectory. False alarm attacks is to change the squawk to 7700. Aircraft disappearance is to just mask completely the messages that are sent by an aircraft. And aircraft spoofing is to modify data from aircraft. We can potentially make any combination of basic operation, modification, creation, deletion, of course. So those, scenarios, you know them probably. The impacts are that the controller can be distracted with false events to hide real events and more potent attacks. We can lose completely an aircraft position, or we can even crash the ATC system. In the VDS, we keep the same definition of the FDIA and we apply it. Like the ADSB, the AIS, which stands for Automatic Identification System, is the cooperative protocol used in the VTS. The main challenge for arbors on individual level are illegal fishing and transshipment. Transshipment is a rendezvous between two ships to exchange illegally goods. FDIAs like spoofing, data alteration, timing attacks to generate slowdown and disruptions also exist. We will dive into the protocol, so the AIS, a little bit more later on. So here are some more realistic, let's say, real-life anomalies that have been detected in the VTS. So for the picture on the left, we find vessels from Senegal turning off their transponder to go fishing in the Gambian national waters and not being seen by the coastal guards. And then they turn them on when they're finished. On the right side, the boat, what we can see on the left, is disappearing on one side of the no-take zone in the Galapagos Island, and then reappear 15 days later on the other side. So we can really think about the fact that this boat actually went fishing in a reserve. So those data are provided by Oceana, which is an international advocacy organization dedicated solely to ocean conservation. So for those anomalies that we've been talking about so far, there are a lot of solutions based on only ASB or AIS data. And those solutions are very often labeled as anomaly or outliers detection solutions. The good things about the solution is that they do not require to modify the infrastructure or the protocol itself, like, for example, encrypting the data, which would take extra step and eventually make the messages longer, which is not really possible. And it's simple to apply compared to, let's say, a model-based testing, which is way too complex to be applied on VTS or ATC. So for a more comprehensive list of efforts made in the literature on the subject of anomaly detection models for ATC, I invite you to go and have a look at the paper cited here. So for now, we decided to really focus on machine learning techniques that are data-driven and that are the bread and butter of anomaly detection models, thanks to the last improvements of machine learning and deep learning, which are very promising, and also because they are really good to manage for managing, big data and the morphology of the data that we have. So machine learning techniques are challenging regarding the data. The data have to be available and of good qualities. Furthermore, the ADSB and the AIS are multivariate time series, which makes not all the methods and models compatible with them, and the models have to be able to handle heavy load of data. Another problem is that the anomalies in real life are rare. We don't see them that often, which makes the datasets for training supervised models uneven, which can create problems for the training, and it makes it even harder to have a comprehensive test dataset for unsupervised models, which makes it complicated to assess really their capacity of detecting anomalies. But first, before talking about the data generation, we'll be a little bit talking about the training data acquisition. Regarding the VDS data gathering, so the AIS, the Automatic Identification System, is a broadcast protocol, just like the ADSB. Its messages are sent from 2 seconds to 5 or 10 seconds, even longer depending on the speed of the bot. So it doesn't have any authentication, doesn't have any encryption, and it's intended to enhance the safety and security of navigation among other protocols that are used as well. So it's used to avoid collision. It's used to monitor the fishing fleets and control it. It's used for maritime security, the aids of navigation, etc., etc. The main issue for the AIS is that there is no raw open data available. Some clean datasets are available, but it's complicated to generalize the machine learning models from it. Global Fishing Watch is an organization trying to make these data available, but usually the country authorities usually prevent them to do so. In our case, we get data from StatSat, which has 4 satellites, but because of their rotation, they usually have way more data on the poles. And we also have data from the Norwegian Coastal Guard. In our case, it's very important to use both sources of data as the satellites get really saturated in crowded areas because of their large coverage and the limitation of the protocol. So we need to use the ground station to have a little bit better granularity. But the problem is that with the ground station, after 40 kilometers, due to the Earth curve, we kind of lose more and more messages. So they are very complementary, and we use the ground station for the coastal area and the satellites for the, well, let's say in the middle of the ocean and seas. Thanks to the efforts from different actors of the community, the raw ADSB data chain is already well defined. With Traffic, the Python tool to query the Impala database, we are able to get raw data that are sent directly by the feeders from OpenSky. Of course, because of that, the pre-processing of the data is needed because OpenSky only treat the data for the stat vectors, and this is not the case for the raw data, so we need to do that ourselves. We'll show that later. And we also try to develop a way to easily feed anomaly detection models. efforts are made to be as general as possible to make the testing of different solutions easier. So as stated in the previous slide, the raw messages need to be cleaned. As we can see on the figures here, the data are quite messy, and this is very complicated to train a model and have an efficient model with time series with outliers such as these. So we try our best to get rid of those outliers, and for now, the best way that we found is to use a local outliers factors algorithm to get rid of those. Now we're going to be talking a little bit more about the data generation for the AI-based model testing and training in the case of a supervised model. Now we're going to present FDIT, False Data Injection Testing, which is our previous work. It's a testing framework meant to evaluate the HCC surveillance system resilience against FDIAs. It also works seamlessly on AIS. So here we're going to present it on the ADSB protocol, but it's just so that it's easier to understand. So we did this to simulate FDIS, but only using the data, whether ADSB or AIS. This means that we collect a sequence of genuine ADSB messages in a file using an antenna or a data provider like OpenSky. Then we import it into the FDIT testing framework to design FDIS scenarios. We apply then a scenario like the squawk changing to transit to emergency, and then we replay the altered recording on the surveillance system under test, as if an attacker has tampered with the surveillance data flow. FDIT, our FDIA testing framework, also includes several modules, such as the surveillance data acquisition, the textual design of alteration scenarios and production of the corresponding set of alteration directives, the configuration of a set of simulated radar sensor. The recording is divided in a set of sub-recordings according to the defined radar sensors, the recording alteration based on a set of alteration directives, and the altered sub-recordings are fed to the surveillance system as if the messages had been received by radar sensors. What's more now is that we added a domain-specific language, DSL. The idea is to include ATC-specific terminology, and we can precisely filter out aircraft. It can trigger alteration based on aircraft-specific events, and it usually tackles the taxonomy of attacks from the literature. Here is an example of an aircraft spoofing. So this is what it looks like. So the DSL is efficient for a productivity boost in a testing context, but it's hardly suitable as is for an AI testing purpose. So from what I said earlier, FDIT seems to be a pretty good candidate to test FDIA detection models. This would indeed allow to generate datasets that contain synthetic but realistic FDIAs. It would allow for the training and the testing of supervised machine learning architectures. It will also allow for the testing of supervised machine learning architectures. And there is the feature of multi-sensors so that we can train and test SDPD and data fusion algorithms. However, since FDIT was initially designed for system testing, new features need to be brought in order to efficiently and effectively generate test datasets for machine learning detection models, such as the labeling of ADSB messages between genuine or altered for supervised learning. It needs to have massification capabilities so that it can generate many altered recordings from one FDIA scenario, and the reusability capabilities, making textual FDIA scenarios recording agnostic. So here is a scenario which contains only one flight. What it does is that it's modifying the trajectory of the flight, only the altitude, triggered when the aircraft is above 20,000 feet. FDIT made recording agnostic, so its start and its end time are related to the recording duration, and the time of passage of waypoints are related to alteration time window, which itself is resulting from the trigger evaluation. The scenario can be applied on any recording, It might not end up with anything interesting on some recording, but no recording specific information is needed for alteration. Now for the use cases. We're going to be showing a little bit of the data sets and the ideas that we can use for the machine learning based FDI detection models. So for the ADSB protocol, several works with autoencoder based anomaly detection model have been made. The idea is to take isolated flights usually with different duration, and messages are grouped by time windows, and we try to encode and decode those time windows, and the ones that are problematic to encode and decode are usually considered abnormals. So the architecture that Habler shows has been used in a similar way by Olive and Bazora to detect events in historical datasets. The Habler model has been easily reproduced by our team, and the results of Habler in previous work can be easily reproduced with by anyone with our architecture. So Abler and all in their paper define several anomalies to validate their approach. These alterations are very basic, and they could be from trivial adversaries. So they include random noise, which multiply the messages by a number between 0 and 2, the route, which replace a whole part of a flight with data of a completely different flight. The drift is to simulate an altitude drift, whether positive or negative. The velocity is the same, but it's a velocity drift. And the block anomaly is to, well, delete some messages in the flight. We also added another anomaly to further test the models with our architecture, which is a trajectory modification, which modify the longitude and the latitude for a long period of time over 100 kilometers, realistically. So most of these anomalies can be recreated by hand, of course, but the automation makes this creation easier and also safer from human error. What we want to do with our architecture is to create more subtle FDIT scenarios based on real life anomalies. So there is a need for better thought out scenarios that are more appropriate for ATC systems like the flooding attack. So we can see an example on the GIF on this slide, which kind of flowed the HEC. We can use engine failure scenarios like the one I showed earlier over Greenland, which force the aircraft to land in different airports. We can also talk about aircraft hijacking. Another idea for a use case is the possibilities to attack targeted data from specific sensors to corrupt this sensor in particular. So it could be used, for example, by the Open Sky team to train models that are asserting a trust factor to feeders so that they know which sensors are trusty or not. So for the VDS use case, we can see different anomalies created by FDIT. So here is a spoofing. So we create several both from one. Here we can see a trajectory modification. So from one trajectory, we create another one here. So that goes through the other side of the island so that we don't know from which side the vessel went through. Here is a rendezvous for transshipment. And here are some normal trajectories. So from our architecture, we get a dataset file with the labels of the attacks and the list of index for the corresponding messages. The data file contains the messages itself. So the model used in here is a self-supervised model using LSTM and transformers, which were out of option before our massification of anomaly data. A submission in a journal is on its way for the model in question. Finally, we're going to be showing the ongoing and the future work. So right now, the idea is to build our own FDI detection model based on generation and self-supervised approaches. First, we want to validate the model with the test data sets obtained from the proposed FDIT generation approach, of course. But we also want to get feedbacks from the model based on the performance to improve the generation, so that the data can go back and forth between the model and the FDIT so that they both improve each other, such as a kind of adversary approach. We want also to do transfer learning between the AIS and LESB protocols because they are really close together and a lot of problematic are shared by those two protocols. We also want to add different type of data to the raw data chains in LESB. So the idea would be eventually to try to find some weather data or to add other modest data to further improve the chain. So we thank you very much for your attention and hope that this presentation was enjoyable. Have a good day.